Thank you, Oscar. And thank you, everybody, for having me here today. I'm going to be talking tonight about whether we can trust ChatGPT or not. And in short, the answer is no. Okay, so if that's all you wanted to know and you want to leave now, you should press for time. That's fine. If you want to stay, I will try to kind of tell you more to convince you as to why I think the answer is no, and also tell you why I think there's still sort of a lot of interesting things to learn about ChatGPT, even though it's not necessarily as trustworthy as its creators might want us to think. So first of all, a little bit of an overview of the talk. I'm going to start by telling you a little bit about me, so you know whether you can trust me or not. Then I'm going to be talking about generative large language models, talking about the hype and the reality and what we get with them at the moment. And then I'm going to be thinking about why. So I'm going to give you a brief history of language modeling and think about how generative large language models actually work. Think about their strengths and their weaknesses and the pitfalls if we're going to use these generative large language models. Talk a very little bit at the end about current work at Sussex, and then also think a little bit about the future. So first of all, who am I? Well, I started life as a computer scientist back in the 90s and moved to Sussex over 20 years ago now. It's very, very scary, to do my PhD at Sussex with David Weir in this field of natural language processing. I'm going to tell you a little bit in a moment about what natural language processing was like back in sort of circa 2000. Since then, I've done a variety of things, including teaching maths in secondary schools. Not particularly relevant, I'm here tonight. But since then, I've become a lecturer in data science. And most recently, as of a few months ago, they decided to make me a professor. So that was kind of nice recognition. Also to say that I co-direct some of these things at the bottom. I co-direct SussexAI, our Centre of Excellence for AI at Sussex, and also Discus, which is data intensive science at the university. And both of those groups of people are kind of largely groups of academics who are interested in collaborating and also talking to industry about the kind of problems that they have with data or AI. Okay, so let's start with a little bit about natural language processing circa 2000 when I was getting interested in the area. Back in the late 90s, NLP researchers were getting excited about statistical methods based on large corpora. And back then, we had this thing called the British National Corpus, which at 100 million words seemed absolutely massive. Okay, it was huge. Well, that's what we thought around sort of late 90s, 2000. And the thing that I came to Sussex to work on was this thing, very obscure problem, called the prepositional phrase attachment, which I'm just going to tell you a little bit about now, just to sort of allow you to think about some of the problems which natural language processing people have typically thought about. So the idea is that if you're looking at these two sentences, I saw the man with the gun and I shot the man with the gun, we've got these prepositional phrases with the gun in both of these sentences. And the idea is to try to work out how that attaches to the rest of the sentence. Is it the man who's got the gun? So it's the man with the gun. So that's what we would typically assume in this sentence, that it's the man with the gun. Or is it the fact that I've got the gun and I'm shooting the man using that gun? So there are two different grammatical kind of readings of those words, even though they have the same, essentially, parts of speech, those words, depending on the meanings of the words, the kind of syntax, the grammar, the way the meaning comes together depends on the meanings of those words. The fact that we are shooting a man makes it more likely that I had the gun, whereas if I was seeing a man, it would be more likely that the man had the gun. So that was the kind of problem that we were interested in back in 2000, and that was, I believe, what I wrote about in my PhD proposal. However, when I came to Sussex, I got sidetracked, as people do when they're doing PhDs, into thinking about completely different things. Well, kind of. because it was related, and this was something that was getting really, really kind of, I suppose, hot at the time, was this thing called distributional semantics, which I am going to come back to later in the talk, as well as we talk about language models. This is actually relevant. And it's this idea which actually goes back to linguists in the 50s, that words that occur in the same contexts tend to have similar meanings. And that's a really important idea in natural language processing and in large language models. So the idea here is that the fact that saw and shot can appear in the same context, that the fact that I can do them and they can be done to the man, and there's this thing with the gun floating around there as well, means that they have a certain similarity in their meanings. And if we look at all of the contexts that words can occur in, we can start to build up this idea of their distribution in a corpus, and then we can start to get an idea of words which mean similar things because they're appearing in lots of similar contexts. So that's where we were back in sort of 2000 to 2003. I'm just going to fast forward a little bit. We will kind of cover the intervening period in a moment, but fast forward to where we are now, which is that now in 2023, that's right, that's where we are. We've got things like ChatGPT and Google Bard, and they're promising us that they can get instant answers and they can give us creative inspiration, all the things that ChatGPT says on its website. And we expect that our kind of NLP tools can tell us anything we want to know. They can rewrite our essays for us. There's lots of things they promise that they can do for us. And if you're in business, you're probably thinking about, oh, how can I use ChatGPT to make my business more efficient, save costs? I can get multilingual support. I can personalize things just by using ChatGPT. It's so exciting. So everybody's very excited about it. And, you know, there's lots of things you can do, even if you're not in business. If you go to, I went to makeuseof.com, and I was sort of thinking, what the people say we can do with ChatGPT? There are blogs that tell you how you can get relationship advice from ChatGPT. I'm not sure I'd want to do that personally. But essentially, anything you want to do or find out about, why don't you ask ChatGPT to create content for you, to help you prepare for a job interview, to write an essay? Why don't you do that? Because a lot of people are doing it. So as I was preparing for this talk, I decided to do a little bit of research, which is something I sort of quite often do, as I'll go to ChatGPT and try and kind of trick it into giving me wrong answers, because that's what I like to do, is try to confound it. And so I thought, well, if I was going to be doing research on a particular subject, what one would normally do, and here I'm sort of thinking about the artist Turner, thinking if I wanted to find out about Turner, you would just look him up on Wikipedia, and you could read the information that you wanted to be able to kind of inform your research. Or now, what might we do? We might just ask ChatGPT the questions of all the things that I want to know. So when did Turner paint a particular picture? And ChatGPT will come back telling me in very good English the year that it was painted, and give me more information about how it was one of his early works and it's significant. And Turner was only 21 years old at the time. At that point, I thought, oh, I'll see if it actually adds up. So that was when I decided to ask, when was Turner born, so I could see whether it had got the years right for him being 21 years old in 1796. That all seems to add up. And then I asked about another picture. I thought, oh, okay, what other things might Turner have painted? Oh, I'm sure he must have painted a picture called The Lighthouse at some point. So I asked, when did Turner paint The Lighthouse? And it comes back again with a really informative seeming answer about how painted the picture titled The Lighthouse in 1817. And it also tells me that this was also known as Bell Rock Lighthouse. And it goes on to tell me how it's one of Turner's notable maritime works. So all this would seem quite useful, interesting, informative answers that are coming back from ChatGPT. But the question is it actually factually correct, what it's telling me? because it sounds like it's coming from a kind of conversation, it sounds like a human's giving you the answer, we tend to believe it. But actually, Bell Rock Lighthouse, the painting, was painted in 1819, not 1817. Only 2 years out. It could have been a lot worse, but it's not, what you would kind of expect. And actually, it's not listed on any of Turner's list of paintings on Wikipedia, let alone any other notable Turner paintings. And there are a lot of other paintings also with lighthouse in the title that I might have been referring to when I said, when did Turner paint the lighthouse? So one might have expected it to come back and say, oh, which painting did you mean? Rather than just assuming that I meant this particular one that it kind of managed to come up with. And actually one of those was painted in 1817. So maybe that's the source of the confusion. Maybe not. We'll come back to that later. But there's certainly something not quite right in its answer there. What else can we do with a ChatGPT? Well, we can ask it to summarize text for us. Sorry, this is a little bit small, especially if you're sitting further back. The actual text here probably doesn't matter too much, and I am going to summarize for you as I speak as well. This is just to show you that this was based on a conversation with ChatGPT. So I asked ChatGPT to summarize some text about Bell Rock Lighthouse, in which I told it the fact that it was actually painted in 1819. And so it managed to summarize it, although I had asked for 3 sentences, and I was a bit picky and told it off and said, well, that's 4 sentences, not 3 sentences. And so it did what ChatGPT always does and gets very apologetic. And then it tried again. And so it managed to do the summarization. But then when you ask it again, oh, is that the right one? Yes, when did Turner paint the lighthouse? It's now telling me that it painted it in 1819. It's changed its mind given the information that I've just given it. And if you push it, it starts to say it apologizes for the confusion. And if you ask it how it knows, it'll never tell you how it knows, I've decided. But it did say, well, it seems to be a matter of some uncertainty. Well, it was uncertain about this. And it does say that you should go to authoritative sources or experts on JMW Turner's work if you really want to know the answers to these questions and to actually verify the correct year. But that all, slightly worries me in terms of the fact that 1, it didn't get it right, and 2, it was quite easily convinced by me that it was 1819 and was quite then happy to say that actually now it was very, very sure it was 1819. Tried again with some other kind of questions, and this one was around Rotherfield, the village where I live, and I was asking it what was interesting about Rotherfield as a village, and it started telling me all about the interesting Tudor buildings in Rotherfield. So I asked it which buildings in Rotherfield are from the Tudor period, and it told me about the old post office, which is this building here, St Dennis's Church, not really Tudor, but as it does say, it does include some features from the Tudor period. And then it also told me about the Six Bells pub. It started ringing some alarm bells because there's no Six Bells pub in Rotherfield. I haven't lived there that long, but I would know if there was a pub called the Six Bells. So I asked it, where in Rotherfield is the Six Bells pub? And it gave me an address in Rotherfield. Slightly worrying what its address, because it tells me it's located on the high street and then gives the specific address as the street, which is inconsistent in itself. And then actually the postcode that it gives is actually from a completely different road in Rotherfield. The pub in Rotherfield, which is Tudor kind of features, is King's Arms, whereas Six Bells is actually, I think, in Chiddingly. But anyway, I kind of persisted with the conversation, told it, well, TN6 3LY is actually North Street. Is that where you mean? And I said, oh, of course, that's where I meant. Thank you for the correction. And then when I asked it again where the Six Bells pub was, it would tell me that it was located on North Street and with the address that it had given. Still telling me to verify the information if I wasn't, if I wanted current details. And when I kept pushing it about telling it that there wasn't a pub called the Six Bells, I think it continued to say, well, its information was only correct at 2021, and maybe the pub name had changed since then. It hasn't. The Six Bells has always been in Chiddingly, and the King's Arms has always been in Rotherfield. So why do we get these inconsistencies and these factually incorrect things out of large language models such as ChatGPT? The reason is that large language models are trained to generate plausible responses, that's believable, ones that you're going to believe, based on very large corpora. Generation does not equal looking up. Nothing gets looked up anywhere in these corpora. It's all about probability, what seems probable as a sequence of words. And plausibility does not equal truth. Just because something is plausible, just because it sounds believable, does not mean it's the truth. So let's think a little bit more about what language modeling is. Anything that's called a language model, the goal is to compute the probability of a sentence or a sequence of words. We're thinking about the probability of this sequence here of n words, or we might be thinking, which is very related, about the probability of the current word given the previous words. Anytime we are trying to compute one of those probabilities, we're dealing with something called a language model. Back in the kind of 1990s and 2000s, when language modeling was becoming popular, there was a lot of motivation for this in various different fields in natural language processing, including in machine translation. So the idea being that if you're trying to translate from your source language into a target language, you want something not that just is faithful to the kind of original information, you also want it to sound fluent in your target language. So you want to pick the sequence of words which is most likely in your target language. So knowing that in English you're more likely to talk about high winds than large winds means that your translation will be more likely to pick the sentence that says there are high winds tonight rather than there are large winds tonight. Or in spelling correction, knowing that the sequence 15 minutes from York is a lot more likely in English than 15 minuets from York would make it possible for a spelling correction system to say, oh, maybe you've got a spelling mistake there, you've mistyped and put minuets by mistake. Or in speech recognition, if you're trying to transcribe what somebody's saying, the fact that the sequence I saw a van is a lot more likely than, and I can never quite say this, eyes or off an, which the speech signal is very, very similar, but it corresponds to a sequence in English which nobody would ever say, allows you to improve your speech recognition results, knowing that this is a lot more likely than this one. So this is kind of like the motivation for doing language model, sort of 20, 25 years ago. And back then, well, even still now, there is the idea of this chain rule for probability, where if we are trying to calculate the probability of a sequence of words, we can do that by thinking about computing the probability of the first word, multiplying it by the probability of the second word, given that we've seen the first word, multiplying it by the probability of the third word, given that we've seen the first two words, and so on. And back in 2000, we imagined that we could estimate these probabilities from a very large corpus. So if I wanted to know the probability of seeing the word hill, given that I've just seen then he appeared over the, we might think, well, I can estimate that as the frequency of the whole sequence, then he appeared over the hill in some very large corpus, and divide it by the frequency of the piece of text here, then he appeared over the, and that will tell me how likely it is to see this word hill, given I've just seen then he appeared over the. Now, the problem with actually doing this, actually calculating these frequencies and using those to estimate the probability is that we have this thing in natural language processing, in language more generally, of data sparsity, which means that these frequencies become really, really small, really, really quickly. Most sequences of words have never actually occurred, so you can't really kind of count them all up and then calculate the probabilities reliably. So what did we try to do? Well, the first kind of step to kind of improving the situation was to do something called n-gram language modeling, where you make these things called Markov assumptions, where you're saying that the nth word depends only on the previous n-1 words. I'll forget all of the ones that happened before that. I would just assume that the probability of the current word depends on only the most recent pieces of text. So if we had something called a bigram model where n equals 2, we'd be talking about the probability of each word depends only on the previous word. We know that's not true, but it's a simplifying assumption that allows us to try to estimate some of these probabilities. But there's still a problem of data sparsity. There's still lots of unseen events in these models. And that led to a lot of work looking at how to smooth probability distributions, which I'm not going to go into now. You'll be glad to hear. And then also there's a problem where vocabulary items are not completely distinct. So you couldn't share probability mass between words that you know are related in some way. At the same time, around the same time, people were getting interested in what I've already mentioned, is distributional semantics. And these two things are going to come together in a moment. And this was this idea that I mentioned earlier, that words that occur in the same context tend to have similar meanings. This idea that we can place words in really high dimensional spaces. I've only drawn 2 dimensions for you here because I can't draw more than 2 dimensions very well on a slide. But the idea is that you have a dimension for every possible context of a word. You can score the words according to how frequently they occur in that context. And you start to see that things which appear very frequently in the same context will group together in the space, and you'll start to see the fact that things which are similar in meaning tend to group together in these spaces. This all starts to come together when we start to talk about neural network language models, where we're going to use a neural network to model the language. We're going to use that to estimate the probabilities of word sequences. Okay? And these are going to be trained on very large corpora. The first of our neural language models goes back to Yoshio Bengio back in 2003, where he proposed this language model based on a feed-forward neural network. The idea here is, whether you're kind of familiar with neural networks or not, but the idea is that we have our inputs here at the bottom, and our inputs are our sequences, our sequence of words. So we've got hole in the ground, there lived, is the kind of piece of text in the corpus that the language model is reading at the moment that it's being trained on. In this feed-forward neural network language model, there was a context window of 3 words. The idea was it would look at the previous 3 words and try to predict what the next word was going to be. So it's looking at the ground there and trying to predict what could come after that in the sequence. If it gets it right, because it actually, our model predicts the word that actually occurred in the corpus next, it will be rewarded. And if it gets it wrong, will have a high loss function, which means that the network will be updated to try to improve its output in future. What's going on in here? Well, essentially what we're doing is each of the words, rather than it just being considered as a distinct kind of input, we have a projection layer where a word is projected into this kind of embedding space, which is going to be shared across the words. And essentially, this is the same as our distributional representations. What we've got I'm going to go on to my next slide, I might come back to that one, is that our word embeddings are points in high dimensional space. It's not quite as large as when we first started thinking about distributional semantics, when we were thinking about all of the possible contexts. But typically, especially back in the kind of noughties, number of dimensions would have been around 300. We'd randomly initialize these embeddings, which would get updated during the training of the neural network. And what would happen is, as they got updated through the training of our neural network, we start to see that the similar words start to get similar embeddings, because we want the output of the neural network to be similar, given the fact that we've got a similar word. So it learns the similarity between these words. And this allows us to generalize a lot better than when we were having completely separate words and we were trying to do our n-gram modeling. Here we're still only looking at 3 words, but we can kind of generalize over the similar words based on their embeddings. Over the years since then, various things have kind of happened, and I'm not going to kind of go into detail about kind of all of them, but just mention a few kind of, I suppose, key points in the kind of language modeling history. Sort of around 2013, recurrent neural networks were getting really popular, and Mikolov, I think it was at Google at the time, kind of proposed this idea of using a recurrent neural network to do language modeling. This was kind of really good because it allowed for essentially got away from us having to have a kind of fixed window of the history of the sentence, because essentially what happens is you have your current word and then you maintain a representation of the sentence history by feeding back the hidden layer as the other input into the network. So essentially you have the current word coming in here, that is combined with the sentence history into the hidden layer, that gets remembered, and then you have your output, which is still trying to predict what the next word is. And at the same time, WordSuffX was another kind of neural network based language model that got really, really popular as a way of creating word embeddings. And essentially, we've got the idea of being able to predict what the current word is given the context, or trying to predict the context given the current word. The idea with all of these is that we're trying to use language modeling and to predict what words are similar to each other, or to build up representations of words and then use those representations to predict what words are likely in the language. There were limitations of using kind of these word embeddings like WordSuffX. Notable ones would be the fact that different senses of a word would always end up with the same representation, so we wouldn't be able to differentiate between star as a celestial body or star as a celebrity. We talk about similar words, but what does similar really mean? That would mix up synonyms, antonyms, class inclusion, etc. So whether words are actually identical in meaning, opposite in meaning, or just related in some other way. There was a lot of work going on at the time as well. It's work that we were doing at Sussex around how do you put these representations together to make representations for larger units of meaning, like phrases and sentences. How do you interpret those dimensions in those spaces? And also, how do you get a representation for a really rare word that you haven't seen very much before? Around 2016, there was kind of further developments in the sort of neural network world, and encoder-decoder networks started sort of taking off. And the idea here is that we're using the recurrent neural networks, such as were popularized sort of a few years earlier, to build up a representation of your input. So you'd have your input sentence here. It would go through a recurrent neural network. So you would get an encoding of that sequence, and you then use that, you decode that into some kind of output sequence. And this is really popular in things like machine translation. We can imagine that we input our sequence of words in English, and the idea is it's trained to output the corresponding sequence of words in, say, French or German. Deep learning was a thing then, it still is now, and the idea here is that essentially it's this idea, but we essentially stack lots of these networks on top of each other. So if we've got our input here going in as je suis étudiant, and we want an output of I am a student, we have stacks of encoders that feed into stacks of decoders to try to get better results. I think the kind of thing that then really started to revolutionize the language modeling community was the idea that came around 2018, and it came with Elmo and also with something called BERT, which I'm going to mention in a couple of slides' time. And this was the idea that when we've got these RNNs, not only can we get a representation of the final sequence out of our encoder, but we're putting it through this kind of encoder, we can think of the output at each time step as being a representation of the particular word. So here I've got the star appeared, and we can think that if we put the star into the neural network, if we look at the output of our forward-looking RNN at this point, it's a representation of the current word in the context of the previous words in the sequence. And we can also go backwards through a sentence. And so what we can do is we can get a representation of a word given the previous words, and we can get a representation of the word given the subsequent words in the sentence. And this is a really kind of nice idea in terms of, rather than having a fixed embedding, which is the same for a word, no matter what its sense is or no matter what its context is here we're saying we want to know what the representation, what's the meaning of star in the current context. And so the idea here is that we would use these representations from the forward and backward RNNs to make a contextualized embedding or representation for a word. At the same time, people started going off of recurrent neural networks, because in 2017, in the machine learning world, they'd kind of come up with transformers and they'd become really popular. Not going to kind of explain exactly how transformers work, but essentially what we're going to see is that we can still have input embeddings. We've got some other kind of machinery here, which isn't a recurrent neural network, but we're still then looking at our outputs. The key in transformers is this idea of attention. And this is the idea that the representation of a word is going to be a mixture of the representations of all of the other words in the sentence. So we saw back with our contextualized word embeddings that we would be thinking about, we would have a representation here, which was based on all of the other words at either side. Here, what we're doing with our transformers and our self-attention is saying that we can learn how much any word should pay attention to any other word in the sentence. And this example is meant to show the fact that when we've got the animal didn't cross the street because it was too tired, the fact the word it, hopefully, if the transformer's doing its job correctly, should learn that it needs to pay attention to the animal because it is referring to the animal there. That's what one would imagine would happen with the kind of attention connections within the transformer. And essentially, any word is a mixture of the representations of all of the other words in that sentence, and attention tells us how much any one of those words contributes to that representation. We've also got the fact that we have multi-head attention. We saw that on the transformer diagram, and the fact that means that it can pay attention to multiple things at the same time. That's the kind of very kind of high level kind of what we've got in a transformer, and that's kind of what is underlying this thing called BERT, which is the first of our kind of what we refer to as our large language models, or our pre-trained large language models. BERT stands for bidirectional encoder representations from transformers. They must have spent a while thinking about how to backronym that one, I think. Essentially, it's the encoder part of a transformer. And what we're doing is we're putting in our inputs, and we've got in BERT base, there are 12 layers, each with 12 attention heads. That's a lot of parameters. I think I've got a slide in a few slides time, which actually kind of mentions the number of parameters in some of these models. But essentially, what something like BERT is trained to do is these general language modeling tasks, very similar to what we were talking about at the beginning. And that's when we're talking about pre-training a language model, it's being pre-trained to do general language modeling tasks. And in BERT's case, it was master language modeling and next sentence prediction. And then you would fine-tune it maybe on a task-specific training data for whatever it is that you're trying to do with your language. So what do we mean by master language modeling? Essentially, it's putting masks on some of the words in your sentence, and you're getting the model to predict what the word should be, or what the word was in the corpus. So if we had the animal didn't cross the something because it was something tired, the model has to try to guess what the word was. That's what we're doing when we're doing master language modeling. We're doing it over very, very large corpora, and we're doing it with these kind of very large models. Typically, it's around sort of 15% of the words that you mask out, because if you mask out too many, then you're not going to have enough context to make the predictions. And if you only mask out, say, one word at a time, it's going to make it too expensive to train. But what you're trying to do is get it to fill in the gaps. And if the word it picks here is, or the word that should be there is one which is highly probable according to the model, then that's good. And if the word that should have occurred there has low probability in your model, that's bad. And that's what you're using to drive the training of all of those parameters in the large language model. The other thing that they did in BERT, which is subsequently, most people don't bother with this with their language models anymore, was they also introduced this idea of next sentence prediction, which was to say, we'll take two sentences. Could they go next to each other in the corpus? Do they follow on from each other? So the man went to the store, he bought a gallon of milk. They were two sentences which were next to each other in the corpus. So the model should be able to predict, yes, it is the next sentence. Or you take two random sentences. The man went to the store, penguins are flightless. They don't really go together very well. So we would want the model to predict that that was not the next sentence. So this idea was to be able to give it an idea of what made coherent text kind of going forward, not just at the sentence level, but how to make coherent paragraphs and documents as well. So what are pre-trained large language models? They are just language models that have been pre-trained on very large corpora. BERT, the one that I've mentioned so far, was pre-trained on Wikipedia, which is 2.5 billion words, and the book corpus, which is 800 million words. At the beginning, I said in 2000, we thought 100 million words was really large. We've obviously got a lot larger than that now. BERT based, and this is one of the smallest, it is probably the smallest of the kind of language models that are out there. If you want to train that yourself on this corpus, that's going to take you 4 days on a 4x4 TPU slice. Not something that many of us have lying around at home or even at the university to play with. And so if you wanted to pre-train BERT, I think I calculated if you were doing that on a single cloud TPU, that would cost around $5,000. So there's a lot of kind of compute that goes into pre-training these large language models. What are the strengths and limitations of something like this? Well, it's going to be strong on the tasks which it's been trained to do. Filling in blanks with plausible suggestions. Identifying whether two sentences are likely to follow on from each other. Where have we got to going beyond BERT? Well, there are lots of variations on BERT. Okay, they mainly have BERT in their name, and some other kind of thing which maybe kind of says something about their kind of what else they do. So Chinese BERTs for Chinese, and Arabert for Arabic. BioBERT is for biological kind of science kind of data. We've got SciBERT as well. That's trained on scientific text, and so on. There are also other pre-trained large language models out there, including the GPT family and other ones as well. How do they vary from what we've kind of been talking about so far? Well, when GPT-3 was kind of released in 2020, the kind of key difference with BERT was the fact that it used something called an auto-regressive language model rather than a masked language model. This is actually what we kind of started with when we were talking about predicting the next word. So GPT models are trained to predict the next word rather than being trained to predict a masked word. This has some benefits and some drawbacks as well. It means that you can have a kind of variable length input quite easily, because if you're using something like BERT, you need to know all of the input at the beginning. But it's also kind of unidirectional in nature. You can't kind of look at what's going to come next in your text to make a prediction about the current word. GPT-3 at the time had 175 billion parameters, which made it 10 times bigger than its competitors at the time. And it was trained on a lot more text as well. So what's happening if you take something like GPT-3 to kind of generate responses to a question, such as when did Turner paint the picture of the lighthouse? You're going to have a prompt, which could just be the question itself, or maybe we convert the question into a sentence where there's a blank that it's trying to fill in, and it's going to try to find words that fill the blanks with the highest probability, given the corpus it's been trained on. That's what it's trained to do. It's not trained to kind of go and look up the answer. It's trained to think what word would most likely go in there. So yes, it may be things which, you know, it's seen occurring near Turner on pictures in the lighthouse before, but it's not trained to actually give you the factually correct answer. Not yet, anyway. So what could possibly go wrong? I think I've kind of already kind of alluded to this. You know, our large language models are trained on fiction as well as facts. Answers can be plausible without being truthful. And large language models are really, really prone to this thing called hallucination, where they just add in words and even whole sentences that just seem plausible, that have a high probability in the context. I think it was one of Turner's notable maritime works, is one of those kind of words which it felt sounded right, because if you're talking about Turner and you're talking about his works, surely you're talking about Turner's notable maritime works. Why would anybody talk about one of his lesser known works? So notable is a lot more likely, because people talk about notable works more. So that would be have a lot higher probability given the kind of training data it's trained on. A little bit more on the kind of theory, because ChatGPT is a little bit beyond GPT-3. What's different when we have ChatGPT? Well, if you go to the OpenAI website, they don't tell you. Well, they actually did tell you a reasonable amount about how they've kind of developed ChatGPT, and they talk about their Instruct GPT models. And there is actually a paper that they released on their Instruct GPT models. And the idea is that they're training these models with humans in the loop, and they're training them to be more truthful and less toxic, using an alignment technique to align the kind of responses it gives to human expectations. And the way they're doing this is using a kind of reinforcement learning from human feedback. And essentially what that means is that customers submit their prompts to the API, and then human labelers provide demonstrations of desirable model behavior, which they then use to fine-tune GPT-3. So they compare what GPT-3 would actually produce with what a human labeler says should be produced. and then say, oh no, you got that wrong, go and kind of try and regenerate something. And so when they're training ChatGPT, they're using the kind of this training data of kind of answers which hopefully were truthful to actually train it to be hopefully more truthful. Various other things in which they use kind of also get the human labelers who work there to rank different model outputs. And use that to also train this reward model. So again, it should learn how likely it is that a labeler would prefer one of its responses to another one. But again, every time you press regenerate or you press thumbs up or thumbs down, you're generating training data for the next iteration of ChatGPT. And then you start to think, well, what about the other people that are kind of going, well, I'm at Bard, I don't want ChatGPT to tell the truth, and they're probably up voting and down voting the wrong answers. So, it becomes a kind of a war of kind of who can kind of, how do we know? How can we verify the training data that is actually going in to some of these models? But anyway, does it actually work, what they're doing? Well, according to OpenAI, it does to a certain extent. Okay, their reinforcement learning technique. So they've got some in their paper and on the website, they advertise the fact that their Instruct GPT model is more truthful than GPT. Although I think 0.413, they didn't really say on the website, I think it does go into it more in the paper, what this is. But if that's an accuracy score, it still doesn't seem particularly accurate to me. Just, yes, a lot more accurate than the original model, but still some way to go. Similarly, in terms of toxicity, so that's the fact that it can generate kind of things which aren't very nice to say, or toxic text. There's a reduction through the reinforcement learning, but there's still obviously some toxic language that will come out of ChatGPT. It's still hallucinating, less than the original models, but it is still hallucinating. And this one's on the kind of, again, similar to the toxicity, whether the language is appropriate for a custom assistant. It, again, has improved it, but there's still obviously some way to go. So when we're thinking about the weaknesses of ChatGPT, we've just got to remember what it is. It is a pre-trained large language model. It doesn't know or understand anything. It doesn't look things up or carry out inferences. When I asked it, I told it that its summary was kind of 4 sentences, not 3 sentences. It didn't then go and count the sentences or do any kind of inferences with my numbers. It just then tried to generate a response that it thought I would like more. And so based on training data where it had presumably been again told about the fact that something wasn't the right length, it shortened its response, but it doesn't actually know how long it is or what that actually means to be 4 sentences or 3 sentences. And it's really easy for it to mix words up, which means similar things, particularly numbers and dates. And we've got to remember that it's been trained on a very large corpus, which is biased towards a certain time period, particular geographic locations, particular cultures and ways of thinking. That is what it's been trained on. And the last thing to remember is that fine-tuning process, I'm not saying it is, but it could be subverted in terms of the kind of way in which we can think about the fact that, does the people that are training it or providing the data, what are their intentions? And that's something we have to kind of remember. It's all about the intentions of the people, not about the model itself doesn't have any intentions. It's just a large language model. It's just thinking about probabilities. What are some of the things that we're doing at Sussex in terms of research in this area? Well, looking at kind of the characteristics of facts and non-facts, which are more likely to be verified or disputed by a large language model. Thinking about how this is affected by asking the large language model to base its answer on some provided text. We're thinking about what type of information is more likely to be generated incorrectly by a large language model. And also looking at things like, does the diversity in the answers it provides, can we measure that and use that as a measure in terms of trying to assess the veracity of what the large language model is telling us? And just as a little tiny flavour of that, some work looking at, this was a Czech COVID data set, which is a publicly available data set, where we're thinking about whether the document provides enough information to support or refute a COVID-related claim. So the idea is you've got a document and then you've also got a claim about COVID, and we are asking ChatGPT to basically, based on the document I've given you, is this claim true? Is it supported? Is it refuted? Or is there not enough information? And it does, reasonably well in terms of, things which should be supported. It says, yes, they're supported. Similarly, even with the refutations, it's quite good. Thing that actually finds it hardest, what we're finding is that when there's actually not enough information in the document, it tends to just guess and say, yes, it's supported, or no, it's refuted, rather than actually just telling you that there's not enough information in the document to make a decision. The future? Well, what does the future look like? I asked ChatGPT, going back to my conversation, and it was quite honest in saying it doesn't have access to current or future events. As its knowledge was last updated in September 2021, I think there is a new version of ChatGPT just come out that's it has been updated a little bit more than that. But it was kind of quite a vague answer. So I thought, okay, I'll be a little bit more specific. I'll ask it, how will people use large language models in the future? It came up with lots and lots of ideas of how you can all use large language models. I've got them on a slide, the next slide as well, so you can see them a little bit better. But it came up with about 15 different ideas, which I have kind of categorized for you here in terms of what I think. ChatGPT suggested all of these as kind of good of how people will use large language models. And I've sort of been thinking about, well, which ones of those are probably okay and which ones are not okay. And so I think in terms of language translation, creative writing, code generation, virtual worlds, gaming, making things more accessible. I think it was talking about how you could, what was it saying with accessibility? Used to make information more accessible to individuals with disabilities through voice assistance, text-to-speech, and other technologies. All of that sounds fairly kind of both plausible to do with a large language model. I think when we start getting into kind of mental health and therapy, I start getting more worried. Decision support, public policy and governance. Please, let's not go that way. I think it would be my personal kind of feeling. Content generation, it doesn't know. Okay, so maybe it's okay to help with kind of how you write something, or creatively writing something. If you're trying to generate something creative, then maybe it's fine to use a large language model. But things which we should certainly be a lot more concerned about how we're using them. If we're using them for content generation, we should certainly be thinking about, how do we verify the content? Does it matter if the content is wrong? And then there's sort of things in the middle, which I'm sure there will be kind of good ways of using them, and maybe some less good ways of using them in terms of kind of recommendations and research and education. Again, I think it's probably good to use them for kind of getting ideas, but maybe the kind of actually doing the research, doing the education, maybe that should be left maybe for a little bit to the humans. Maybe we should wait a few more years before we have the AI doing all of the research for us. And certainly not a large language model. Okay, that's all I've got to say. And then say, are there any questions?